All right, let's get started. I've got the handouts for you here. Remember that the introductory assignment that I gave you in class last time is due before noon on Friday, so that means you need to stop by during my office hours and we'll chat briefly. It should only take maybe 3 or 4 minutes, and that'll give us a chance to get acquainted. I'd like to know more about your background, your interest in engineering, and it'll give you a chance to break the ice and not be nervous about coming to talk about a professor and coming to talk to the professor in his office. Your homework assignment here, homework 2A. So chapter 2, problems 2, 7, 11. The problems are numbered like 2.2, 2.7, 2.11. So it's just, these are all problems from chapter 2. And that's due in class at the beginning of lecture on Tuesday the 2nd of September. So stack them right here at the beginning of class, stapled and ready to go. Sometimes there's a stapler in here, but sometimes not. In fact, I'm not seeing it now. So you can't count on the stapler being here in the classroom. There is a stapler in the technician's office, an electric one that you're welcome to use, but don't come in here with loose papers expecting there to be a stapler because it looks like somebody's walked off with it. It's a sad day. All right, so any questions on these announcements here? We're going to talk about elasticity and viscosity today. And elasticity is a property that has to do with changes in volume due to an increase in pressure that's applied to a fluid. And there's a property called the bulk modulus of elasticity that describes how this is going to happen. The bulk modulus is a way of saying for a change in pressure how much of occupied volume is going to change. And so think about a cubic meter of water. If you had an element of water and applied a really high pressure to it, and we're not talking about small pressures, we're talking about enormous pressures to be able to compress water. Water is generally considered to be incompressible. By the way, were there extra handouts at the end of the paper, at the end of the table there? The bulk modulus says that if you have a certain applied pressure, how much of the original occupied volume is going to change. And so for water, it's 2.2 times 10 to the 9th pascals. And just looking at units, a pascal is the same as a Newton per meter squared. That's a unit of pressure. And so it says that if you apply really high pressures, that you can have some minor change in volume for water. Another way of thinking about it, the bulk modulus that is if you have a change in pressure, what is going to be relative to the original volume, the change in volume. Now the negative sign that's in front of the bulk modulus means that an increase in pressure is going to decrease the volume. So let's try and put this in practical terms with a small example here. If we have 5 gallons of water, then apply 5 megapascals of pressure to it, then what would be its volume in liters in that case? And so the first thing we'll do here is just convert the 5 gallons into liters. So if we have an original volume of 5 gallons, remember the conversion table is at the beginning of your textbook where it says that there is 3.785 liters per gallon. Okay, so we start off with an initial volume of 18.925 liters. So what will be the volume in liters if a pressure of 5 megapascals is applied? Okay, the bulk modulus of water is given. We need to rearrange this equation to find for the delta V. So the original equation tells us that the bulk modulus is equal to negative delta P times the volume times delta V. And so we have that the change in volume is equal to negative the pressure that's applied times the original volume and the bulk modulus of elasticity. Okay? We know that the pressure that we're applying, we have the negative sign because that's built into the formula. The pressure that's applied is 5 megapascals. Okay, so that is 5 million newtons per meter squared. And our original volume in question is 18.925 liters of water. Now the bulk modulus is 2.2 times 10 to the 9th newtons per meter squared. So when we pop that into the calculator, we find that the change in volume is going to be a reduction of 0.0430 liters. Okay, so the final volume, if we started off with an initial volume of 18.925 liters, then the final volume, after applying that pressure, is 18.925 liters, and then the change is a decrease, 0.043 liters. 18.882 liters is the final volume. So it didn't change much, and we're applying pressures that are just really high. A typical pressure in a drinking water distribution network, for example, would be maybe 500 kilopascals. So this is an order of magnitude beyond that, and it still occupies most of its original volume. Okay, so any questions about what elasticity talks about? Just in lay terms, you might be thinking of it as the compressibility of water, or what is the relationship between the pressure that's applied and how much it compresses. All right. So what do you suppose this is a picture of? What does it look like? It looks like honey, right. The little air bubbles there. Why are those air bubbles visible? If we were pouring water out of a spoon, you wouldn't be able to see air bubbles like that. Why is it visible in honey? Is it some special chemical thing having to do with it being sweet? Okay, what does viscosity mean? What? Resistance to flow? All right. We usually think of honey as being very thick or very viscous. You know, another example to contrast the ordinary viscosity of water, another contrast to that is oil. If you're pouring oil into the engine block, it pours more slowly out of the container than if you were pouring water into your engine block. Hopefully you'll never do that. Don't make that mistake. But this honey in this photo, the reason why those air bubbles are entrained like they are is that the fluid, the liquid of the honey is so viscous that the buoyant force of the bubbles isn't enough to rise out of the surface. So let's take a look at a little video that illustrates concepts of viscosity. The default Flash player being Internet Explorer is not ideal. Let's see if maybe I can get it to play with something else. I think we've got VLC on here. Is it going? Open. Every time they re-image the machines, I lose the ability to do something else. I've got an idea. I know what I'll do. I'll open it on my desktop in my office. All right, so if we calculate the force on the top of the plate, it's going to be the viscosity of the fluid, the area of the plate, and du dy. So we looked up right in the given information there that the viscosity is 0.15 Newton seconds per meter squared. The cross-sectional area of the plate is 6 square meters. And now the velocity that we're shooting for is 0.58 meters per second. And the distance between the top of the tank and the plate is 1.2 meters. So we use 1.2 as the dy. And from that, we get that it is 0.435 newtons. And the force on the bottom of the plate, again, is going to be the same formula, the viscosity times the area times the rate of strain. And so the viscosity is still 0.15 Newton seconds per meter squared. The cross-sectional area is still 6 square meters. And the rate of strain is going to have 0.58 as the velocity, but a larger distance, 2.4 meters, and that will bring the force down to 0.2175 newtons. Therefore, the total force is 0.6525 newtons. It's the sum of the forces that are acting on the top and the bottom of the plate. So this is how much we'd have to pull on the plate in order to achieve a velocity of 0.58 meters per second. If you pulled on it harder, then it's just going to reach an equilibrium with a higher velocity. So think about the type of quiz questions that I could ask you that make use of this formula. It might be that I give you a force and I give you the velocity and the distances, and from that you can calculate the viscosity of the fluid. Or it could be where you are calculating the cross-sectional area based on all the other given information. Basically, any one of the variables in this equation could be the unknown. Any questions on that example or about viscosity in general? Well, since we're only pulling on the plate from one location, the force of the fluid on the plate is transferred from this entire surface to just the one point of connection. And so it doesn't matter if the force is on the top or the bottom, it's all being transferred into this cable that we're pulling on it with at a single point. And so we have to consider, the resistance that's acting on the plate wherever it's coming from. Viscosity actually is independent of pressure. So a couple of the initial responses that we had today was mentioning the fact that in a channel that the pressure is greatest at the bottom, and that's true. And pressure is going to be really important for a lot of the problems that we solve. So if this is air, as you go down through the fluid, obviously the pressure is increasing, but what's not increasing is the viscosity. It doesn't matter if we're talking about some of the water at the top or some of the water at the bottom, the viscosity stays the same. It is a function of the fluid itself. Water has a different viscosity from oil, and it's definitely a function of temperature, but it's not a function of pressure or location inside of a flow field. It arises out of molecular forces, and in a liquid, the cohesive forces decrease with increasing temperature. That's why a fluid becomes less viscous when you heat it up. The interesting thing is that with a gas, if you look in the figures that show viscosity as a function of temperature, the gas viscosity actually goes up. as pressure increases. Not pressure, as temperature increases. And so, can I borrow this for just a second? All right, so here's absolute viscosity as a function of temperature, and you can see most of these curves are going from the top towards the bottom as the temperature increases, and these are the liquids. But for the gases, there's just a very slight increase as the temperature goes up. And the reason for the increase is because as the molecules get more active and bump into each other more, that increases the molecular activity and increases the viscosity, because it's, I guess you could think of it as it's harder to make your way through the gas as their collisions increase. It's getting more crowded in there because of the greater increased activity of the molecules. So here's an illustration of both air and crude oil showing the function of temperature on kinematic viscosity. Now, there are these really interesting fluids called non-Newtonian fluids. And a Newtonian fluid is where shear stress and shear strain has the relationship is not affected by the shear that's applied. A shear thinning fluid like toothpaste or ketchup, you may have noticed that if you have a glass bottle of ketchup, if you shake the ketchup is able to move out of the bottle more easily than if you're just holding it steady. And it's partly because, as you shake it, you're applying a greater force than just the force of gravity if it's sitting there. But actually, the properties of the fluids themselves change as you apply the force. The fluid gets thinner when you shake it. It's not just that you're applying a greater force, but actually ketchup gets thinner as you shake it. Its viscosity is decreasing. There are also things that are called shear thickening fluids, and that is, as you apply a greater force to a shear thickening fluid, then its viscosity goes up as a response to that. We'll look at a video of that in a second, but the figure that is important to look at, this is showing shear strain and shear stress, and a Newtonian fluid, like water, for example, has a linear relationship. The viscosity doesn't change as a function of the force that's being applied, but some fluids will have their viscosity react to the forces themselves. So let's look at this video, if I still have it. I can't believe I deleted that. I think I've got something else. Let's see. I had to move it off of my V drive because it was taking up too much space, but I must have kept a copy of it somewhere. This will have to do. Okay, this is a mixture of cornstarch and water. And what people will sometimes do is they'll put this liquid onto a vibrating speaker, like put a piece of plastic over a subwoofer that's vibrating. And the vibrations of the subwoofer makes this mixture of cornstarch and water solidify. It's a liquid that just sort of would pool out, but then when you start applying the movement from the subwoofer, then it sort of congeals together and it becomes much more viscous because of the mixture. Its viscosity increases. me see if I can find a different one. Love the so it's watch YouTube videos all day, but we won't. The textbook appendix, like I've mentioned, has all the fluid properties that you could want in one convenient place, and you'll need that for the homework. Now let's change subjects a little bit and talk about gas laws. And you probably have some memory of the ideal gas law from when you were taking chemistry. There will be a couple of times where you need to find out the weight of gases based on its temperature and the amount of moles of gas present and so on. So PV equals nRT, where R is the universal gas law constant. We can rearrange the ideal gas law and isolate the pressure variable, and if we substitute in the definition of the molecular weight of a gas, which you can look up using the periodic table. For example, the molecular weight of hydrogen gas is 2 grams per mole. Molecular weight of oxygen gas is 32 grams per mole, and so on. So if you know the molecular weight of the gas and you substitute in the gas law constant, basically what it ultimately leads to is an expression that has the density, the specific R for the gas in question. This is not the universal R. This is an R. Every gas has its own R constant. The absolute temperature. And so you can find out the pressure of a gas based on its density, R value, and temperature. Where it comes up is when we are trying to find the physical properties of a gas in a room. Like in this instance, we say there's a room that is 4 by 5 by 6 meters, and we want to find out what is the density of the air in the room when it is at a pressure of 100 kilopascals, which is roughly the atmospheric pressure. Actually, atmospheric pressure at sea level is 101.325 kilopascals, but this is pretty close to typical sea level pressure and room temperature, approximately, maybe a little warmer than room temperature. But let's go through this using the gas laws to find out what is the density of the gas, what is the mass of air that's present in the room, and the specific gravity, which is a term that we had last class time. So first of all, if we look at the R value, we can get the R value for air out of table A2. And R is given as 287 joules per kilogram Kelvin. And that's kind of a strange unit. Just to take a look at what those are in the base units, remember that a joule is the same thing as a Newton meter. So that's like a Newton meter divided by a kilogram Kelvin. And remember, we talked about earlier today that a Newton is a kilogram meter per second squared. So this is the same thing as 287 kilograms meter per second squared. So what was Newtons is now kilograms meter per second squared, and we still have the meter, the kilogram, and the Kelvin from before. And if we cancel out the like units here, the kilograms cancel out, then we're going to have 287 meters squared, second squared, and Kelvin. All right. So the pressure is given in the problem statement as 100 kPa. And that's the same thing as 100,000 Pascal. And a Pascal is a Newton per meter squared. So this is 100,000 newtons per meter squared. And a Newton, remember, is a kilogram meter per second squared. So it's 100,000 kilogram meter per second squared. And we still have the meter squared from before. And we can simplify that by canceling out the meters here and the squared there. So it's 100,000 kilograms second squared and meters. And then the temperature that's given in the problem statement of 25 degrees Celsius, we have to convert that into Kelvin to be able to use it. And so if we add 273, it is 298 Kelvin plus 273, which is the conversion to go from Celsius to Kelvin. Okay, so we want to find out, first of all, what is the density of the air in the room. And from the earlier combination of the ideal gas law and the R value, we found that density can be calculated by the pressure in the room, the R value, and the temperature. And that will enable us to calculate the density of the gas. So the pressure is 100,000 pascals, or 100,000 kilogram second squared times meter. The R value is 287 meters squared per second squared Kelvin. And then also the temperature is 298 Kelvin. Okay, so hopefully all the units are going to work out here. We know that density, just from our past experience, we know that density should have units of kilograms per cubic meter. One way to know if you're using the right equation is check the units to make sure it all cancels out the way that it should. So we've got the Kelvin in the denominator here and Kelvin in the numerator for this term, so they're going to cancel each other out. Okay, we've got seconds in the denominator of a denominator, and so it's going to come up here into the numerator, and the seconds are going to cancel out. And so we've got kilograms per meter and meter squared down here, so it is going to work out that the units are kilograms per cubic meter as we need them to be. And so if we do the calculations, it's 1.169 kilograms per cubic meter is the density of the gas. All right, that's the first part. Next, it asks, what is the specific gravity of the air in the room? Does anybody remember what's the definition of specific gravity, or SG as we abbreviate it? It's a ratio, but what is it a ratio of? All right, good. So it's going to be, in this case, the density of air relative to the density of water. All right, we just calculated that the density of air was 1.169 kilograms per cubic meter. Density of water is what? Have you memorized that one yet? How many kilograms per cubic meter? 1,000. Good. If you don't have any other specific information about the temperature, that you need to go look up the density in the table. If it's just the typical density, it would be 1,000. Now, the air here is at 25 degrees Celsius, but we're using typical water temperature as our density baseline. So the specific gravity is 0.001169. And finally, what's the mass of air in the room? Well, we know the volume of the room through calculating 4 times 5 times 6 will give us the volume, and we want to multiply that by the density to find the mass. And so the volume is 3 times 4, why do I keep saying 3? It's 4 times 5 times 6, 4 meters by 5 meters by 6 meters are the dimensions of the room, and that is 120 cubic meters. And we multiply that by the density of the air, which was 1.169 kilograms per cubic meter. And in total, there is 140.3 kilograms of air in the room of that size. So that room's not probably, I don't know, roughly the size of this room, maybe smaller. This room's maybe smaller than that, but ballpark, there would be about 140 kilograms of air in this room. If you look up the universal gas law constant, it's available in so many different units. And in every single example I work through this whole semester, I'm always going to include the units as I do the calculations. I'm going to do that to try and set an example for you to do the same thing. When you're working on your homework, don't just write the numbers. Write the numbers and the units that go with them. Because if you forget to include the units, sometimes inevitably you may end up using the wrong constant when you're looking up a constant. The way to know whether you should use 8.31 or 1.98, how do you know which one of those to use, is you look at the other units in the equation that you're substituting the constant into and look at what are the other units in there and what needs to be canceled out. So I'll try to remember to always include the units in the examples that we work together. All right, that's all that I have for you today. Let's just take a final look at these announcements. Remember that you need to stop by my office. I've got office hours today through much of the afternoon, and then also about an hour and a half tomorrow where you can stop by and do that introductory assignment. You've got homework assignment 2A due at the beginning of class on Tuesday, and also the lab assignment is due in lab on Tuesday. And so that separate packet where you're supposed to take a look at the lab report, analyze it according to the rubric, and then the second part of the lab assignment is to identify some potential safety risks and what you can do to avoid them. Question, yeah? For your homework assignments? Yeah. It would be better if it's engineering computation paper, although I know that it's more expensive. There will be times later on in the semester where that's particularly important when we do flow visualization. Another question? Yes, yeah, please type the lab. Yeah. Thanks, guys. I'll see you next Tuesday.